All right, so we know now about, thank you, functions and combining functions and composing functions from yesterday, right? Which is basically what happens if we take one function and plug it into another function, right? That's what we looked at yesterday, or like doing two or more in sequence, right? One after the other. One of the ways that we can sort of use that or see where that comes up, the idea of composition, is in inverting a function, which just means like undoing, right? So that's what we're going to look at today, how we find an inverse to a function, or again, like really the idea is undo a given function. So to kind of build up to that idea, first we're going to think about inverting just single operations, right? So just what the opposite operation to some of these things would be. So go ahead and get into groups, talk about these things for just a second. What would be the opposite to multiplying by 7 or dividing by -3 or whatever? Okay, so we have, yeah. No, yeah. So we have 5, fairly simple, not a lot going on, things that work at and preserve that like function relationship we've been talking about, right? So for example, multiplying by 7, if you give me a number, give me a number. 4, okay. 7 times 4 is 28, right? And sometimes 4 is always 28. It's not 28 sometimes and 46 other times, right? So multiplying by 7 does preserve that function relationship, right? The rest of these things do as well. So they are functions. What we're looking for is the opposite or the inverse action to these things. Basically, what would you have to do to, Colby gave me 4, I multiplied it by 7, I got 28. What would I have to do to 28 to get back to 4? Divide by 7, right? Okay, so the opposite or the inverse action to multiplying by 7 would be divide by or dividing by 7. I guess if I want to match the tens. Okay, so the opposite or the inverse action to dividing by -3 would be multiplying by -3. Okay, so if it's just a single arithmetic step, then it's, the thing you think it is. Multiplication, division, those are inverse to each other, right? Those are the same thing, but in opposite directions. Addition and subtraction would be the same thing, right? Same idea. Putting on a jacket. Taking off the jacket. Okay. You see how we're kind of getting at the idea of function composition here too? If you think about doing, the one that's written there, the one's on the page, and then our version of what the inverse would be, if you do one after the other, where do you end up? Colby, you gave me 4. If I take 4, multiply it by 7, I get 28. If I divide that by 7, I get back to 4, right? Okay, so if I start somewhere and go here, in the middle I get this. If I go there, I get back to 4, right? So I end up back where I started. The 4 is not important. The same thing would happen for any number I started with, right? Okay. Same thing happens with these others. Take a number, divide by -3, multiply that answer by -3, you get back the original number, right? You start with no jacket on, you put on a jacket, then you take off the jacket, you end up again where you started with no jacket on, right? Okay. Composition is doing one thing, then doing another thing, like sort of immediately after, right? Okay, what about something that has multiple kind of steps involved? Putting on socks and shoes, right? And those would happen in that order, right? I mean, for most of us, maybe do weird things, I don't know, but most of us put on socks, then shoes, right? How do you undo that? Take off your shoes, then your socks. Okay. Taking off shoes, then socks. Okay, well, really, that's an order of operations thing, right? That we're undoing the individual things, right? Undoing the steps, but we're also sort of walking the order in reverse, right? We gotta flip the order of the steps around as well. Again, if I do one of these and then the other immediately afterwards, I end up back where I started, right? If I'm barefoot in the first place, I put on socks, I put on shoes, then I take off my shoes, then I take off my socks, I end up barefoot again, right where I started. Okay, what about multiplying a number by 3 and then adding 1? What has to happen to undo that? Subtract 1, then divide by 3. Try it real quick. In your group, pick a number, multiply it by 3, then add 1, see what you get. Then take that, subtract 1, and then divide by 3. You should get back to whatever number you started with. Okay to work? Okay, cool. So that doesn't, necessarily like prove that those things are really inverses to each other. It just proves that it works for whatever number you chose. I chose 7, it worked for me, so I guess now you know 2 numbers maybe. But that's the idea. What an inverse needs to do is reverse the individual steps, if possible. We'll talk about that. And also reverse the order, right? So it's sort of opposite operations in reverse order. Okay. So that last thing, multiplying a number by 3 and then adding 1, if we get into the like order of operations stuff and how we would write that down, well, the number that you choose, I could call that X or any other like variable, right? For the number that you choose. What I want to happen is for it to get multiplied by 3 first and then add 1. Well, luckily, order of operations stuff, multiplication comes before addition anyway, right? So if X is my number, then something like 3X plus 1 does that for us, right? Take your number, multiply it by 3, then add 1. So here is a function, an equation, a symbolic form for this thing that does what we just described. Multiply by 3, then add 1, right? Everybody agree? Everybody happy with that? Okay, so how would you write a thing that does the opposite? Take a second, think about how you would write down a function, write an equation like that takes a number takes a number that you give it, subtracts 1 first, and then divides that by 3. All right, so the potential like problem or the thing we got to deal with is that normally subtraction happens after division would, right? And normal like order of operation stuff. So how do we fix that? Yeah, parentheses or some kind of grouping symbol, right? That's the way you force things to happen in a different order is you group them up. Okay, so if X is my number, I need to subtract 1. So X minus 1, right? And then I want to take that, the result of X minus 1 and divide that by 3. So how can we write this? X minus 1, throw a set of parentheses around it. Divided by 3. Okay, you could write it like that. Most of the time, we don't use the little division symbol, right? Typically, more often, we're going to see that written something like this. And the fraction bar, or writing division like that, we treat the stuff on top and bottom as though it's in parentheses anyway. So most of the time, we would just drop those as well. So fraction bar acts like a grouping symbol, just like parentheses. So here you would do the subtraction on top first and then divide that by 3. Okay. All right. So there's a blank set of axes right there underneath that. Graph those two functions together and graph them with your calculator or Desmos or whatever, and just sketch them on there. Try to do it like a little bit carefully, but I would graph them both in Desmos and kind of see what they look like there, or in your calculator and see what they look like there. So graph both of those together, and then, well, I'll let you read directions and follow. once you got the graphs together, talk about, anything that you notice. We'll get some points, maybe, might help. I've seen all the things people are using straight A's. Calculated. All right, so there's one of them, right? That's y equals 3x plus 1. So, again, it's a straight line, looks like that. The other one looks like this. It's also a straight line. I also asked you to graph y equals x. I said to do it as a dotted line or dashed line, but there it is. If I throw all three of those on there together, and again, I'm going to ask just sort of a vague question, but do you notice anything? Okay, they all cross, right? And all three of them cross at the same point, right? It's not that, two of them cross at a time in different spots. They all share one point in common. And because they're straight lines, right, being straight lines, that's the only place they cross, right? After that, they go off and do their own thing. So, okay, that all crosses at one point. That's kind of interesting. Anything else? Kind of opposite? Yeah, I like that. Okay, symmetric relative to that dotted line. What do you mean, Theo?
It's the same distance from the dotted line.
Pick a spot to kind of focus on. Use the dotted line as your reference. So kind of turn your head to the diagonal maybe. If you go out this way and out this way, that's the same distance away, right? And the same thing's going to happen kind of wherever you go. Okay, that's interesting. Let's maybe look at a point or two. I mean, if you want to think about linear function stuff, we haven't really talked about that, but you've seen it before. Think about slope. What's the slope here? 3. Okay, so you're going up 3 for every one that you go over, right? This one, the way it's written, it might be a little bit harder to spot, but that's 1/3, right? 1/3 x. So the slope's 1/3. So you go up 1 for every 3 you go over, right? Okay, so again, we get kind of that idea of them being, opposite, relative to that line, or symmetric relative to that line. The intercepts for the blue one, whichever one that is, the one we came up with, the intercepts are 1, 0, and 0. That's -1/3, right? That's the x and then the y intercept. Here, the red one goes through 0, 1, and -1/3, 0. Well, those numbers look familiar, right? But what's different? The coordinates have switched places, right? Well, what's going on there? When we're thinking about a function, what are x and y? What do x and y do? How have we been using x and y to talk about functions? Functions here, right? X is the thing that you sort of give it as input, right? And then function does its thing. It turns out a y value that goes with it, right? Okay, so what's going on when we go from one of these lines Like focus on 0, 1 maybe. When we go from one of these to the other, the X and Y switch. That's like the thing that was the input and the thing that was the output switching places. What are these two things supposed to do? These two functions? It's supposed to, you start at a number, right? You start at a spot, you do the things, then you undo the things and you end up back where you started, right? Okay, so if these things are inverses of each other, opposites of each other, then what should happen is if I start at 7 and go through the first function, it gives me back 22. I take 22 and sort of go backwards and get back to 7, right? Or, you know, whatever other number. So let me draw a picture. If this is our function f, it takes an x and spits out a y. What this new function that we just came up with does is basically reverse that process, right? Works backwards. We're going to call that the inverse. And the way that we write the inverse is with a little -1 superscript. So it sort of goes in the same place that like an exponent would. It's not a power, it means the inverse, and again, you treat this as the inverse of f or f inverse. And again, what it does is it's a function in its own right. What it does is undo exactly what f did, right? So just like we saw, you know, here with me plugging in 7, doing both the things, and then getting back to 7, if they're really inverses to each other, then they would do that for any value that's in the domain of the original thing, right? You would be able to sort of go back and like go through one, compose, so do the other one, and then end up back where you started. Okay, questions about anything so far? Think we're okay with that idea? Okay, so take those same two functions, and on the back here, a couple things to do. So I've labeled the thing that we started with, 3x plus 1, I've labeled that as f. I've labeled this thing that we're that we think is the inverse, the x minus 1 over 3, I've labeled that as g. Plug 5 into f, and then take the result of that and plug it into g. And then go the other way, plug 7 into g, and then take the result of that and plug it into f. Again, in both cases, you should end up back where you started, but just check real quick that you do. This is, you know, sort of two separate things, like an A and a B. Once you've done that and shown that like it works for 5 and for 7, then we want to see if it works in general. The way we see if it works in general is to actually compose the two things. So find f of g and find g of f. And for the sake of time, let's maybe focus on, you work down sort of these two problems on like the left-hand side of the page. Then you do the other two as homework, but so work on those two things. All right, everybody convinced that it works for 5? Start with 5, you do 1, take the answer you got there, you do the other, you get back to 5, right? Okay. What about composing the two? Right, so finding f of g of x. That would mean f of x minus 1 over 3. So if you haven't already, go ahead and run through that. Check that. Or check to see what that gives you. All right, so if f is 3x or f of x is 3x plus 1, then what's f of x minus 1 over 3? It's 3, and in place of x, I put that whole thing, right? X minus 1 over 3. Right, we're composing, so we're plugging one function into the other. Right, the order says do g first, so plug g into f. Okay, now that we've done the substitution, right, we've plugged it in, now we just need to simplify. So what can I do to simplify that? Cancel the 3's. You're multiplying and dividing by 3, so cancel those. We get x minus 1 plus 1. Combine like terms, and what do you get? X. Okay, what does that mean? Like, cool, we pushed all the symbols around, we ended up with just x. What does that actually say, though? Think about, look back at the problem just above it, too. Oh, Logan, go ahead, what do you got?
Whatever number you put in for x is just gonna.
Yeah, what we just did when we composed, composing is, one function then the other, right? Composing is laundry. So what we just did in the problem above this is started with 5, and we did 1, then we did the other one, we got back to 5, right? I don't really care that it's 5. This says if I do one function, then the other, right? Do g, then do f with anything, right? Now we're doing it with a symbol, right? We're doing it with an arbitrary thing that stands for all kinds of stuff. This says if I do it with anything, I get back what I started with, right? It's not that I care about the x, it's that I care about that this and this are the same. And it's not just that it happened to work for 5 or it happened to work for 7 or whatever, right? I got lucky when I picked a number to pick in or to plug in. It's that it works for anything, right? That's what we've just shown. The fact that these are the same means that this works for anything. As long as the functions are defined, as long as we're like in the domain of the things, it's going to work for whatever you want, right? So the stuff on the right-hand column there where you're doing the same kinds of things, the only difference is that you're doing it in the other order, right? If two things are really inverses of each other, then it shouldn't matter if I go this way, or this way to this way, right? They should both do the same thing. So what you should find, what you will find here when you go through the composition is the same thing. This is going to give you x back after you plug in and simplify, do all this stuff. Yeah. Do what? So it's g of f now, right? So you're going to be finding g of 3x plus 1. So plug 3x plus 1 into g, do the algebra, you should end up with just x back. Okay, so that's the sort of final thing. If two functions are inverses, that's what should happen. Because being inverses means that one undoes the other, or that they swap X and Y values, or that they're symmetric across that line Y equals X, the line Y equals X, because if you flip across that line, what you're doing is swapping X and Y. Okay, so the things that we still need to kind of talk about are like, when can we do that? And how do we find one in general, apart from, because this whole thing that we've been going through has just been the fact that I was able to take this description and switch it around, right? So what's it mean to be a function? How do you check to see if a thing is a function? If each input, each X value has one output, one Y value. Graphically, that's testing vertical lines, right? If it passes a vertical line test, meaning a vertical line test never hits it more than once, then you're good to go, because that's an X value, and you're checking to see if it hits more than once, does it go with just one Y, right? Okay, so if I take vertical lines and flip all the X and Y values, or reflect them across the line Y equals X, what do they turn into? Think about what all the points on a given vertical line look like. They all have the X coordinates the same, right? Like every point on this line would be, maybe 5 comma something, right? If I switch all of those coordinates, if I take every single one of those points and switch the X and Y values, what do you get? A thing where all of the Y values are the same, right? It's a horizontal line. So things that pass a horizontal line test, which we call one-to-one functions, have an inverse. Here's a picture to show you why. Suppose that's our original function. If I hold that line still and flip it over, what do you get? It's going to be that same kind of shape, but facing which way? To the side, right? It's going to flip the whole thing over sideways. Is that pink thing I just drew a function? No. Well, if that's not a function, then the thing I started with must not be one-to-one, which again just means it must not have an inverse, right? Because having an inverse would mean that I got to be able to like reverse the process and get back to where I started. Think about the blue, the Y equals X squared. It goes through like the Y value 4 in a couple different places, right? So if I try to reverse that process, I don't know if 4 came from 2 or from -2, right? That's the problem we run into. I don't get like one answer back. Okay, so that's how we check to see if a function is one-to-one. To actually find the inverse, if we can't just sort of reason through it like we did before, then what we do is swap the X and Y values and then solve for Y. So what I would do is take something like this, right? Think about it as Y equals 1 minus 2/3 X. I would rewrite that as X equals 1 minus 2/3 Y, right? Because what a function and its inverse do is swap input and output, or swap X and Y. So write it as X equals 1 minus 2/3 Y, and then solve for Y. Okay, so do that one for homework over the weekend. We'll pick up there Monday and talk about that, and then maybe work through one more or something. But that's the idea. That'll at least get you started on the 6.1 stuff. You have a good weekend. I'll see you on Monday.